So we're continuing with the wave equation. So here's a quick recap of the conclusion from last time. That here we have our PDE, the wave equation, and defined on the entire real number line. So this is a Cauchy problem, no boundary conditions. And because of the second order time derivative, we have two initial conditions. So this is modeling a vibrating string. So U is the displacement of a string, and f of x is the initial displacement. And then du dt is the velocity of a string, so the initial velocity is given to be some function g of x. So for this problem, what I derived last time was this solution formula. So the Lembert's solution, we see that's a combination of graph transformations of f, and then this integral of g from x minus ct to x plus ct to get the solution u of xt. The constant c that comes from a coefficient of a PDE represents the speed of wave propagation. So what we have here is a wave propagating to the right, and here we have a wave propagating to the left, just because this is a rightward shift of the graph of f. This is a leftward shift. So we have two-way wave propagation. So what we're going to see today is how to interpret this solution to get an idea of how the solution behaves over time for certain cases. And then we'll take a look at the semi-infinite problems. What if it's my laptop, but the Cisco WebEx app just died. Okay, I'm going to rejoin the meeting. Not sure what happened there. Okay. I'm not sure what's going on down in Gulf Park. Okay, I guess we're need to deal with this echo. Okay. Nope, still echoing. Dang it. I'm sorry. I don't remember how I've dealt with this in the past. Okay. Oh, nope. One second. Testing. Dang it. All right, I think that made it work. Let's see, got my notes on the screen. Anyone who is connected to a meeting who is attending online, could you please tell me whether you can hear me? I need to know.
Yes, we can hear you.
Okay, thank you. Okay, technology is not my friend today. Okay, so we'll see how it's a good idea how a solution behaves based on this formula for certain situations, and then afterwards we're going to look at the problem of semi-infinite string, where we're only considering the PDE on the domain 0 to infinity. So we have a boundary condition at x equals 0 in this case, and then we'll talk about some boundary conditions. Okay, now, one thing I want to point out, and I need to fix this real quick on the, not the Canvas site, but the other website. So this week I'm covering lessons 18, 19, 20. So I'll be talking a little bit about 19 today, but I will not be assigning homework problems from lesson 19, just 18 and 20. I had some problems posted from lesson 19 on the external site, and I'm removing those right now, just so there's no confusion as to what the next homework assignment is. Okay, let's try to get this tank show on the road. I feel like in the middle of a Looney Tunes frustrated Daffy Duck or something. All right, so we're going to look at two cases that are simplified versions of the original problem. So here, these initial conditions will have some given initial condition for the initial displacement of a string, but a zero velocity. So that way the solution formula just reduces to this. So half the initial data is propagating to the right, the other half propagating to the left. So that idea of how a solution behaves, so the idea to find a solution at any point xt, what you can do is start from a point xt and then navigate along these two lines. So x minus ct is equal to x naught minus ct naught, x plus ct is x naught plus ct naught. So it turns out that the solution at a point xt, it comes from the initial data at a point x naught t naught. Right. So, and I'll show you graphically what that means in a moment. But I want to give you an example of initial data. So suppose the initial data is 0 most of the time, except between minus 1 and 1, where it's equal to 1. So we just have this square wave at the beginning. So, okay, I need to unshare and reshare so I can show you the picture from the text. All right. Okay. All right. Now, here, if we look at on the x-axis, between minus 1 and 1, that's the only place where the initial data is non-zero. So, in QI, this is the xt plane. So t is playing a role of vertical axis. So suppose I pick a point xt, let's say in this region right here. Then, to find out what the value of the solution is, I'm going to travel along this a line with this slope that's parallel to these lines that you see here, that corresponds to x plus ct is equal to a constant. So for my point xt that's right here, let's say, as an example, I'm going to follow this line down to the x-axis. And because it lands between -1 and 1, I have 1/2 the value of the initial data at whatever point I land at. Similarly, from my point xt right here, I'm going to travel along this line that's parallel to these right here, corresponding to x minus ct equals a constant, down to the x-axis, which will put me somewhere over here. Now out here, the initial data is 0, so I'm getting no contribution from over here. So value of the solution u of xt at a point xt right here is half of the initial data over here, and plus half the initial data from over here. So what you're doing is, from your point, wherever it might be, you're drawing lines from that, starting from that point, that has a slope of plus or minus 1 over c. And that comes from these equations right here. X plus ct is equal to a constant. X minus ct is equal to a constant. So these lines, if you think of t as playing the role of y, have a slope, so change in t over change in x, of minus 1 over c for these lines, and then plus 1 over c for these lines. So if I choose a point here in this triangle down below, for a very small period of time, I follow lines going in this direction, that both will land between -1 and 1. So in this triangle, the solution is equal to 1. In these bands, the solution is equal to 1/2, because if I follow lines of slope -1 over c and 1 over c, I'm going to pick up initial data from one direction, but not the other. So that's why in these shaded regions, the solution is equal to 1/2. Anywhere else, outside of these bands, the solution is equal to 0, because if I'm out here, for instance, in this region, and I draw a line of the appropriate slope from here down to the x-axis, going in this direction and going in this direction, no matter what, I'm going to land outside the interval -1 to 1. And therefore, the solution is 0. All right. So this leads to the concept of what's called a domain of dependence. That at a given point xt, the solution at this point can only depend on initial data in the cone that comes from drawing the triangle that comes from drawing a line down here and down here, and anything in between is the only part of the domain that can influence the solution at the top of a triangle. Similarly, if I think of a point, consider a point on the x-axis, like right here, then there's a concept called the cone of influence, that the solution here can, at t equals 0, can only influence the solution in a portion of the xt plane, where if I take, starting from this point, if I draw a cone that has this boundary on the left, this boundary on the right, anywhere in that cone can be influenced by the initial data at the tip of a cone, but nowhere else. So it's very different behavior than, for instance, a heat equation. If I have initial data from a heat equation that behaves just like this initial data, where it's 0 everywhere, except in some interval, like -1 to 1, then as soon as t goes positive, the solution to the heat equation is non-zero everywhere. It may be very small, but it's still non-zero. That's not true of a wave equation. So out in this region here, because the initial data is 0, the solution will remain 0 outside of these bands. All right. Any questions about how the values of the solution in these different regions is arrived at? possible I might have a better picture for you. Let me check. What I'm showing you here is a textbook from another PDE course we have here, Math 606. That's only for the graduate level. But it covers a lot of the same topics. So we want some wave equation. Okay, this helps. So here's an example of what I was talking about, domain of dependence. Here's a point, x naught t naught, at which I want to know what the solution is. So if I draw lines of, in this case, slope 1 over c and minus 1 over c, for whatever c is, that only the initial data here in this interval between these two dots can influence the value of the solution here at this point. Okay, so they call it region of influence. But it has the appearance of a comma. So at a point, this point A, the initial data at this point can influence the solution in this region between this line and nowhere else. Here with the initial data B can influence the solution in this cone, and where it intersects, for both A and B will have an impact. So we see here that the initial data is discontinuous. There's a jump discontinuity at x equals plus or minus 1. It follows that the solution will also have a jump discontinuity, because here it's equal to 1/2 in these regions. Elsewhere it's equal to 1, and then everywhere else is equal to 0. So this is also a distinction from a heat equation. If the initial data to the heat equation is discontinuous, as soon as t becomes positive, the solution will immediately smooth out. So whereas here it does not. Now here's a different situation where the other part of the initial data is non-zero. So here we have no displacement initially, but we do have some given initial velocity. So du dt is equal to some g of x. So then we have the other half of our solution formula right here. U of xt is this integral of g from x minus ct to x plus ct. So so now suppose we have the same kind of initial data where it's equal to 1 between minus 1 and 1 and 0 otherwise. Here it's a bit tricky to figure out what solution is going to behave like. It's a little more complicated than the last case. So I have another picture to show you. Okay, so now we have these numbered regions, 6 numbered regions in all, where a solution has different formulas. And this now, whereas the initial data is piecewise constant, now the solution will be a function of x and t, but different functions of x and t depending on where you are. So the idea is this. When we look at the solution formula, you're integrating from x minus ct to x plus ct, but keep in mind that this initial data is only non-zero between minus 1 and 1. So really there's 2 intervals to consider. You have this interval, where it's non-zero, and then this interval from a solution formula. Really what you're doing is you're figuring out the intersection of this interval and this one. And that is where you'll evaluate your integral. And since the additional data would just be equal to 1, it would just be the difference of those limits. All right. Now, so what we have worked out is, so what you can see here in the textbook is, for different regions, 1 through 6, what the integral actually reduces to for this given initial data. And what we can see is, for regions 2, 3, 4, 5, 6, notice the limits have changed. In some cases, the lower limit is 1. In some cases, the upper limit, sometimes the lower limit is 1, but minus 1, that's what I'm trying to say. Sometimes the lower limit is minus 1, not sure why that minus refused to get out of my mouth. And sometimes the upper limit is equal to 1, just because of where the initial data happens to be non-zero. Okay. So, I'm going to give you an example of how these integrals are arrived at. So I'm going to, as my example, I'll use this one, region 2. So if I go back to the picture, so let's suppose my point, I want a solution at some point xt that falls somewhere within this region 2. So let's suppose right where my arrow cursor is, let's suppose that's where the point is. So now I need to look at, if this is my point xt, so I'll go ahead and see if it'll let me mark it. No, I don't want to do that. Okay, this one. All right, so I'm going to mark a point right here, x t, make it a little smaller. Okay, so from this point, I'm going to draw a line with this slope, so parallel to these lines you see right here. X minus ct is equal to a constant. So, and I would trace it all the way back down to the x-axis, so t equals 0. So from here down to here, and then also a line with this slope. So parallel to these lines are x plus ct is equal to a constant. So this goes down here. Now, what happens is, normally I would find x minus ct, which is somewhere over here, x plus ct, which is over here, and I would integrate g from here to here. But here's the problem. X minus ct in this case, traced down here, is outside the interval minus 1 to 1. So over here, the initial data is 0. That's why the lower limit of the integral for a point in region 2 is going to be minus 1. So I really start here. Whereas starting from here, if I look at x plus ct, and go down all the way down to the x-axis from here in this direction, this does fall within the interval minus 1 to 1. So that's why the upper limit of the integral remains x plus ct. So that's why I'm integrating from minus 1 to wherever x plus ct is, which is somewhere in here. So then I take the, and since I'm integrating just 1, I'm just going to take the difference of these two limits. So now I'm going to have 1 plus x plus ct all over 2c. And sure enough, that's the solution solution formula for points that are in this region. So we have 1 plus x plus ct over 2c in region 2. Same thing in region 4, except we have a minus. Where these two regions overlap, we're going to get t. That's my solution. Then 1 over c up here between the two. And then outside of all of this, the solution is equal to 0. So in general, you are integrating from x minus ct to x plus ct, but you have to modify these limits if g is happens to be 0 in a portion of this interval. There are questions about how these kind of solution formulas were arrived at. I'll show you, I'll mention one more. Like suppose I'm in this region 6. So I have a point somewhere in this triangle. So then I draw lines to the x-axis from that point. So down here, down here. Both of them are within the interval -1 to 1. So that's why the limits of the integral will remain x minus ct and x plus ct. And that's what we have here for region 6. This will be the integral. Since, in this case, both of these values are between -1 and 1. So then I'm integrating 1 over this interval, so I'm just taking the difference of the limits. The x's will cancel, and I'll have ct minus ct. So I get 2ct over 2c, so that just simplifies to t. So that's why the solution is equal to t in this triangle. And so for figuring out the different scenarios, it's very helpful to have a picture like this. It'd be kind of difficult to do without it, honestly. So when I was looking at this, I noticed there was a typo in the textbook. So for a previous picture where u is non-zero and at the initial data and udt is 0. And it says solution to initial value problem 18.1 in the xt plane. That should actually read, this right here should be 18.3. It's this problem right here. All right, now we're going to look at semi-infinite string. So same PDE, except now we're on the domain 0 to infinity. And now we have our general initial data. And then we have a boundary condition. In this case, u of 0, t is 0. So it's a type 1 boundary condition imposed at x equals 0. So I'd like to come up with a solution formula using a similar approach to what I showed you last time. And we can start out doing exactly that. So this part is exactly the same as before. We're defining these new variables, c and eta, to be x plus or minus ct. And so in these new variables, we get this PDE, derivative u with respect to c, then eta is 0. And that would be, have this general solution. So just like before, it's going to be a function of x minus ct plus another function of x plus ct. We just have to figure out what those functions will be. And it'll turn out to be somewhat different than last time just because of the boundary condition being added. So far, nothing is different yet from last time. Now, when we enforce the initial conditions, like I did last time. This is what we have from before. But oh, why not just use this? Well, here's the problem is, f and g are only defined on the intervals 0 to infinity. What if, for a given x and t, x minus ct is negative? So this formula, psi of x plus ct, this is fine, because if x and t are non-negative, and certainly x plus ct is non-negative, we're good over here. But for this case, if x minus ct is positive, again, we're good. But we have to account for a case where x minus ct is negative and do something else. All right. So how do we deal with that? We use a boundary condition. And so far, we haven't actually used it. That's a red flag right there. So if I go to here and enforce the boundary condition on this equation, that means I'm just setting x equal to 0. And the result must be 0, because that's what our boundary condition is. U of 0t equals 0. So when I do that, this is what I get. So 5 minus ct plus psi of ct is 0. Now, this is the term that is problematic, because I can't have anything with a negative argument due to x and t being restricted to positive values. But now, I don't need to worry about this, because I know what phi of minus ct is. It's minus psi of plus ct. So my function has a negative argument. I can write in terms of the other function with a positive argument. So what that means is, this part of my solution that was problematic due to the x minus ct, I can now write as this. Minus psi of whatever argument you have negated. So if x minus ct is negative, then ct minus x will certainly be positive. And this is something that I'll be able to evaluate. And this, I know what it is, because I solved for it earlier. This came from the same process that was used last time to solve for what would become the elaborate solution. So applying a function for a formula for psi from a previous page, I get this. So now, whenever x is less than ct, this is my solution formula. So psi of x plus ct that I had before, and then phi of x minus ct is now equal to this. So now I put all that in here, and I get something that closely resembles the Lambert solution formula. But look at the differences. There are 3 of them. Well, 2 of the differences are, wherever you had x minus ct in the previous formula, you now have ct minus x. And the other difference is, here we had a plus before, now we have a minus. So whenever x is less than ct, you use this formula. Whereas if x is greater than or equal to ct, well, go ahead and use the elaborate solution. It's not a problem in that case. You don't need to be concerned about the boundary condition there. So really we have a piecewise solution formula. So this one for x less than ct, this one for x greater than or equal to ct. So here's the dividing line where x is equal to ct. So when x is greater than or equal to ct, so over here, you just use the old solution formula, the inverse. Because notice that this region out here has nothing to do with the boundary. When x is less than ct, we're over here, and the alternative formula is used. And watch what happens because of the boundary condition. U is equal to 0 at the boundary. So we have a wave propagating to the left, it bounces off. So the Dirichlet boundary condition introduces reflections against the boundary x equals 0. So that's the effect on wave propagation of this boundary condition. Because without this boundary condition, this wave would just keep going all the way up to minus infinity, but the boundary sends it back. So if I look at this point, x naught, t naught, I want to know what the solution is here. In the old case, a Cauchy problem, the solution at this point would depend on the solution down here, following this line. And then I would take this line and follow it all the way down to the x-axis and use initial data from here. So half from here, half from here. But because of the boundary, I'm following this line until I hit the x-axis, the t-axis, then bouncing off, and the initial data over here is what affects the solution at this point. Okay. One thing I want to point out from one of the homework problems from this lesson, lesson 18. The problems I assigned, I actually want to make sure of that. Okay. Yeah, problems 1 and 3. Okay. All right, so this problem. So this is similar to the problem I've just been talking about. With one key exception, we have a different boundary condition. Du dx is equal to 0 at x equals 0. So that's going to result in a different solution formula again. So that's something to be careful about. So where it would come into play is right here. So this is what I get from enforcing the type 1 or Dirichlet boundary condition. U of 0 t equals 0. But for the polar problem, you're not going to get this equation. It's going to be different. Because you're going to be taking derivatives of all these with respect to x and you're still going to be solving for one of these, for phi in terms of psi, but it won't be exactly the same. So I've had students work out this problem and they turn into the exact same thing as for a type 1 boundary condition. It's not. Trust me, it's not. If that's what you get, you did something wrong. But the general process is the same. Now, this is sort of a setup for what I'll talk about on Wednesday. What if we're on a bounded interval? So we have boundaries at x equals 0 and x equals L. Now, as far as how you solve this problem, you do use a separation of variables like process, and that's something I'll get into on Wednesday. But I just want to talk about the boundary conditions. So here, the type 1 or Dirichlet boundary conditions. U is equal to some given function g1 at x equals 0 and some given function g2 at x equals L. For most problems, these would be 0, but there's always a possibility of non-homogeneous boundary conditions, which you know how to handle for a heat equation, and you can carry out a similar process for a wave equation. Right. So in this case, we have a fixed displacement at x equals 0 and x equals L that leads to these value conditions. Or you can have a force specified on the boundaries. So vertical forces are given by these values where T is a tension. This could lead to, for instance, if ends of a string are allowed to slide, then these are boundary conditions. So they're not tied to a fixed point. So these are, these as type 3 boundary conditions from the heat equation discussion, also known as Neumann boundary conditions. So Dirichlet is when the solution is specified at the boundary. Neumann is when technically the normal derivative, but in the case of one space dimension, it's just the derivative with respect to x is specified on the boundary. And then if the ends of a string are attached to springs, and you have mixed or Robin boundary conditions, so both u and du dx play a role. So it's kind of like from a heat equation where you have the temperature of the medium specified instead of the temperature of the rod. So boundary conditions have the same form. Where in this case, theta 1 the functions are given. Theta 1 and theta 2 are the displacement of the spring attachments at each end. Not sure where a solution will come about in nature, but mathematically it leads to this boundary condition. You might have different boundary conditions at each end. We saw that in the heat equation too. So it could be Dirichlet at one end, Neumann at the other. That would affect your eigenfunctions from your Sturm-Liouville problem when you carry out separation of variables. That part is no different from the heat equation. Because heat equation versus wave equation, the spatial ODE is exactly the same. It's the time part that is different. But that's something I'll get into more on Wednesday. One thing I want to point out about homework for this part, this week's material. There are some problems that ask you to sketch a solution at various times. I'm not, for a grading standpoint, I'm not interested in that. So that's part of the direction. Okay. I'm going to come to the end of the notes. Our questions about this or about the homework problems. I know I have some homework ready to catch up on. I'll be sure to do that by the weekend. A better way to start spring break now. Okay, I guess we'll call it good. More time to prepare for next class.